Assalamu alaikum dear students. Today we are going to start the article number 10.7. This is about power series. Now this series is a little bit different from the series we have already done. We have already done with the series consisting of numbers. Now we are going to discuss the series with variables. So let's see what is power series and how can we check the convergence divergence of the power series. So first of all, we'll define power series and then we'll check the convergence. There are few theorems about convergence and the radius of convergence and multiplication of two power series, term by term differentiation of power series, and term by term integration of power series. So first of all, what is power series? You are already familiar with the structure of polynomials. If we have an nth degree polynomial, then it can be written as an x to the power n plus an minus 1 x to the power n minus 1 plus an minus 2 x to the power n minus 2 and so on a1x plus a naught. So this is a polynomial of degree n, right? And you are already familiar with this structure. Now, power series is quite similar to the polynomials, but it has infinite number of terms in powers of some variable. Now, in this case, these a's are constants, right? So let's define formally the power series. Now that we can test many infinite series of numbers for convergence, I have already told you, we can study some sums that look like infinite polynomials. We call these sums power series. So infinite polynomials, sums of infinite polynomials, such expressions, such series are called power series because they are defined infinite series of powers of some variable. In our case, this variable is going to be x. So like polynomials, power series can be added, subtracted, multiplied, differentiated and integrated to give a new power series. So with power series, we can extend the methods of calculus to a vast array of functions, making the techniques of calculus applicable in an even wider setting. So here is the formal definition of the power series. A power series about x is equal to 0. So this is very important. About x is equal to 0. This x is equal to 0 is the center of the power series. So a power series about x is equal to series is the series of this form sigma cn xn where n varies from 0 to infinity. Now you can see that this looks like a polynomial but its degree is infinite, right? So this is the general definition of power series about x is equal to a, where a is any real number. And it can be defined by this series, sigma cn x minus a to the power n, where n varies from 0 to infinity. And this is given in equation 2. Now, if we have a power series in this form, or a power series about x is equal to a, then a is called center and these constants c0, c1, c2, cn are called coefficients. So equation 1 is the special case obtained by taking a is equal to 0. So this is the series with center x is equal to 0. We'll see that power series defines a function fx on a certain interval where it converges. Now, we have already dealt with the series with numbers. So, a series in numbers, if it converges to a number. Now, in this case, we have a series in variable. So, if it converges to some function which depends upon this variable. So, let this function be fx. If series converges, then the series converges to a function fx for some value of x, and that some values of x actually consists an interval. So moreover, this function will be shown to be continuous and differentiable over the interior of that interval. So first example, let's have a series sigma n is equal to 0 to infinity x to the power n. So what was the general form of the series? Sigma cn xn with center x is equal to 0. So This is the special case of this series with Cn is equal to 1 for all n. So if Cn is equal to 1 for all n, then this series becomes this series 1 plus x square. If you see the structure, you can easily say that this is a geometric series. And a geometric series converges if its common ratio, that is r, is less than 1. Now in this case, first term is 1 and r here is x. So this series will be convergent if r is less than 1, that is if x is less than 1. So this series is convergent if x is less than 1. Now what is the sum of the series if x is less than 1? We know that the sum of geometric series is going to be a, that is first term, over 1 minus r. Now a in this case is 1, so sum of the series here is 1 over 1 minus x. So in this case, the fx we were talking about in previous slide, fx here is 1 over 1 minus x. So this series converges to fx, which is equal to 1 over 1 minus x if x mod is less than 1. This is very important to note. Otherwise, this series might be divergent. So here we go. Since this series is convergent, converges to this fx, so this fx is equal to the convergent series. So in this case, 1 over 1 minus x is equal to this geometric series, where x lies between minus 1 and 1. Now, let's have a look at partial sums of the series. In order to check whether this series converges to this function 1 over 1 minus x. So we will draw this function along with its partial sums of the series, and we will see how this series converges to the graph of this function. Now partial sums of this series are the polynomials p and x. So let's consider different partial sums of the series. That is, p and x in this case is going to be 1 plus x square up to xn, right? So here is the figure. So what is p naught in this case? And Pn is denoted by Yn. So P naught, that is, we are just going to take the first term, which is 1. That is, y naught is equal to 1. So y is equal to 1 gives us this line. You can see this line. This is y naught is equal to 1. Now, if you see that center is 0, when x is equal to 0, this function has the value 1. Okay, and the exact graph of this function is shown in this by this blue line. So at this point, the value of this function and this function partial sum is equal. So at x equal to 1, this function has value 1. That is, this point is 0, 1. When x is equal to 0, that is the center, x is equal to 0, then y is 1. This is the point on the graph of the function. Now, if you see, when we have y is equal to 1, this line passes through this point, that is this center. Now, next we have y1. y1 is going to be 1 plus x. 1 plus x is also a 9. Now, y1 is equal to 1 plus x. Now, at x is equal to 0, this y1 is 1. Again, 0, 1 lies on this line. So, at center, all these sums approximate this function very well. Not only center, rather in the neighborhood of the center, these sums approximate this function very well. But as we move further from the origin, we can see that there is a lot of error, right? So this is the line and there is the point. So if you draw this, and you can see that what a huge difference of the value of the function at this point and the value of the y at this line, right, where x is same at both the points. So there is a huge error. Now as we increase the degree of the polynomial, that is, we increase the value of n, we can see that the graph of the partial sum is quite closer to the exact graph of the function. So this is what we conclude, that for values of x near 0, we need to take only a few terms of the series to get good approximation. But as we move towards x is equal to 1 or x is equal to minus 1, we must take more terms in order to have good approximation. So we can observe this from the figure. So the function fx is equal to 1 over 1 minus x is not continuous on the interval containing x is equal to 1, where it has a vertical asymptote. So the approximation do not apply for x is greater or equal to 1, or you may say x is greater or equal to 1, right? X is greater, that is on the right side of the interval, or on the right side of the 1, approximation is not good at all, rather it diverges. So because at x is equal to 1, this is not defined, at x is equal to minus 1, this is defined. So we cannot say this. Actually I said for this, but this is not the true case. This statement is true, that is, the approximation do not apply for x greater or equal to 1, only for this region, right? This region. Okay, next example number 2. We again have a power series, and this power series center is 2. So x is equal to 2 is the center of this series, and the nth term of this series is minus 1 over 2 to the power n x minus 2 n. So in sigma notation, this series can be written in this form, where n varies from 0 to infinity. So C naught in this case is 1. C1 is minus 1 by 2 if we compare it with the previous series when we define the infinite series with center x is equal to a. So a here is 2 and all these ci's are given, where Cn is given by minus 1 by 2 to the power n. Now you can again see that by the pattern that this series is geometric series with first term 1 and ratio is x minus 2 over 2, negative of x minus 2 over 2. Now again, if this is a geometric series, this will converge if r is less than 1. R is less than 1 means x minus 2 over 2 must be less than 1. So in order to find the interval for which this series is convergent, we have to solve this inequality. That is, x minus 2 over 2 is less than 1. Now in order to solve this inequality, let's have a look at it. We can expand this like this. You have learned it in calculus 1. So this is how we can write this inequality. Now we can multiply the inequality with 2 because 2 is positive, so inequality will remain same. So we have minus 2 less than x minus 2 less than 2, and in order to find the value, in order to find the range for the x, we have to eliminate this minus 2, that is, we have to add 2 in the whole inequality. So left side will become 0, less than this will central term will become x, and this will become 4. So this is the interval for which this series is convergent. And what is the sum of the series? If the series is convergent, sum is going to be the first term divided by 1 minus r. First term here is 1, So R here is negative of x minus 2. So by plugging in the values, sum of the series is 2 over x. So we can write 2 over x is equal to this series. Again, you can see that the sum is the function of x, that is sum fx. Now, since this series 4, generates useful polynomial approximations of fx is equal to 2 over x for the values of x near to. Now again we can check by the partial sums of this series that near to these partial sums approximate the series very well. But as we move further from 2, we can see that we have to add more values, or we have to take higher value of n. We have to consider higher value of n while taking the partial sums, right? So this is the graph of original function in blue, okay, and this is the graph. This line is the graph y naught is equal to 1. This line is the graph of y1 is equal to minus 1 over x. But you can see that what is common in all these approximations, that all of these approximations pass through the center. That is, at x is equal to 2, what is the value of 2 over x? At x is equal to 2, value of 2 over x is 1. So what is the point? 2, 1. So every approximation passes through the point 2, 1. So this is what we can observe again. Now there is another example. Example number 3. For what value of x do the following series converge? Now we have already considered 2 examples. Both of them actually turned out to be geometric series. Now there is an example. This is not a geometric series. So see what we are going to check the convergence of the series. So this is the series sigma minus 1 to the power n minus 1 xn over n, where n varies from 1 to infinity. And term wise, this series can be written in this form. Now we can apply root test or ratio test. So in this case, let's apply ratio test to the absolute series. So for this we have to find the limiting value of un plus 1 over un mod. So un plus 1 over un becomes n over n plus 1 x mod. So as n approaches to infinity, this part approaches to 1. So as n approaches to infinity, this ratio approaches to x. And by ratio test, we know that this series will be convergent when x mod is less than 1, right? So this series converges absolutely when x mod is less than 1. So we have one interval for which this series is convergent, and diverges when x mod is greater than 1. Now what about x is equal to 1 and x is equal to minus 1? So for this we have to check individually. For x is equal to 1, this series becomes an alternating harmonic series, and we have already seen that this series is convergent. And at x equal to minus 1, at x equal to minus 1, we have this series which is negative of harmonic series. And since harmonic series is divergent, so this negative of harmonic series is also divergent. Okay, what we have concluded that this series will converge when x is less than 1, greater than minus 1, and this series is also convergent at x is equal to 1. So we are going to put equality here. So this is the interval where this series will be convergent, and this series is divergent elsewhere. And we can prove that the sum of this series is log of 1 plus x, and we'll prove it later on. So there are the comparison of the partial sums and the original function. You can see it yourself. So here we go. This is the interval of convergence. Minus 1 is not included. Minus 1 to 1, where 1 is included. That is, this is half open, half closed interval. Minus 1, 1, right? There is another example. Sigma n varies from 1 to infinity minus 1 to the power minus n minus 1 x to the power 2n minus 1 over 2n minus 1. Again, we are going to apply the ratio test, and ratio test, this ratio un plus 1 over un converges to x square as n approaches to infinity. Now, when will this converge? When this ratio is x square, so this will converge when x square is less than 1. Okay, so this will converge when x square is less than 1 and diverges for x square is greater than 1. Again, what happened when x is equal to 1 and x is equal to minus 1? So we will see it individually. So first of all, we have concluded that the series is convergent for x square is less than 1 and for the divergent for x square is greater than 1. Now at x is equal to 1, the series becomes 1 minus 1 over 3 plus 1 over 5 by plugging in the values in this series, x is equal to 1. So we have this series which converges by alternating series test, and you can check it yourself. It also converges at x is equal to minus 1 because it is again an alternating series that satisfies the conditions of convergence, alternating series convergence. So the values at x equal to minus 1, the negative of the values at x equal to 1, so series B converges. So this means this series converges and in the closed interval minus 1, 1. So what we have discovered so far, series can converge in an open interval, series can converge in a semi-open or semi-closed interval, series can converge in a closed interval and diverge elsewhere. Now part C, so let's see what part C has in store for us. In this part, we have the series sigma xn over n factorial n varies from 0 to infinity. Again, we are going to apply the ratio test and we see that this ratio converges to 0 for every x. So the series converges absolutely for all x, right? Now in the last part, so in this case, notice that this series is convergent for all x, that is x lies between minus infinity and infinity. And what is about this next series? In part D, we have this series n factorial xn, and which can be written in term wise in this form. Again, we are going to check with the help of ratio test whether this series converges or diverges. So un plus over un gives us this result, and this approaches to infinity as n approaches to infinity unless x is equal to 0. So the series diverges for all values of x except x is equal to 0. When x is equal to 0, this converges to 0. And otherwise, as n approaches to infinity, this approaches to infinity. So we have only one point of convergence for this series. And for rest of the values, for rest of the real numbers, this series diverges. So the previous example illustrated how a power series might converge. The next result shows that if a power series converges at more than one value, then it converges over an entire interval of the values. The interval might be finite, infinite, contains one, both, or none of it endpoints. We have already seen in all these examples. We will see that each endpoint of a finite interval must be tested independently for convergence or divergence. So here is the theorem number 18 about the convergence of power series. So if we have a power series of this form, a0 plus a1x plus a2x square, and its center is x is equal to 0. If this power series, now if is important, if this power series converges at x is equal to c, where c is not equal to 0, then it converges absolutely for all x with x mod is less than c mod. If the series diverges at x is equal to d, so it has two parts. If the series diverges at x is equal to d, then it diverges for all x with x mod is greater than d mod. So it has two parts. First part, if series converges at x is equal to c, where C is not equal to 0, that it will converge in the interval, open interval minus C. Okay. And next part, second part is, if the series diverges at x is equal to d, then it will diverge for all the values where x is greater than C or d, right? So let's see how can we prove this. So the proof uses the direct comparison test. So we'll use direct comparison test in order to prove these results. So we'll prove first result first. So suppose that the series, now since this is given, the given power series is convergent at x is equal to c. So if this is convergent at x is equal to c, that is, this series is convergent. Sigma an cn is convergent. We just replaced x by c. So then the limit an cn is equal to 0 by nth term test. As n approaches to infinity, this term will be approaching towards 0 by nth term test, since this series is convergent. Hence, there is an integer n such that an cn mod is less than 1. Right? Now, since this series is convergent, this condition will also hold. So, an cn mod is less than 1 for all n greater than n. So that we have, now from this inequality, we have an mod is less than 1 over c mod to the power n for all n greater than n. Now take any x such that x is less than c, x mod is less than c. So this implies x mod over c mod is less than 1. Now we consider any x in the interval minus c. Okay, we consider any x in the interval. So any x in the interval will satisfy this condition. X mod is less than c mod. So this inequality gives us x mod over c mod is less than 1. Now multiplying both sides of the equation by x to the power n, we have x to the power n, an is less than x to the power n over c mod to the power n for all n greater than n. Now since x over c is less than 1, right, x over c mod is less than 1, and this is a geometric series, right side is a geometric series, it follows that this geometric series, this is the actually nth term of the geometric series. So this geometric series will converge since x over c mod is less than 1. So this geometric series will converge, and we can see that x n a n is less than x over c to the power n. That is, by direct comparison test, we have an is less than bn, and bn is convergent, right? So we can say that this series is also convergent. Sigma x and an also converges. So the original power series, since this converges absolutely, so the original power series also converges absolutely for x lies between minus c and c. So this was the claim in the theorem. So first part has been proved, and you can see this by the figure. This is the interval where this series converges, and this is in next part we will see that this is the area where the series will diverge. Now in next part we have to prove if the series diverges at some point x is equal to d. Okay, if series diverges at some point x is equal to d, then it diverges for all x where x mod is greater than d mod. So we suppose that sigma a and xn diverges at d, which is actually given. If x is a number with x mod is greater than d mod, then the series converges at x. Then the first half of the theorem shows that the series also converges at d. Okay. Now if we assume that, we assume otherwise, right? This is given that this series this series is divergent at x is equal to d. Now we assume that the series converges for some x such that x mod is greater than d mod. Okay, but from the first half of the theorem, it must converge at d as well. So this is contrary to the assumption or contrary to the fact which is given. So the series is divergent for all x with x mod is greater than d mod. So from all the discussion done previously, we can conclude that the theorem we have just proved and the examples we have studied, which leads us to the conclusion that a power series sigma cn x minus a to the power n behaves in one of three possible ways. Number one, it might converge only at x is equal to a, or converge everywhere, or converge on some interval of radius r centered at x is equal to a. Right? So you can see all the situations given in this diagram. So this converges only in this interval which centered at a, otherwise divergent, and this is convergent only in the half open, this is the closed interval, and in this case half open half closed interval, and in this case again semi closed interval. This is the case where series is convergent in an open interval. This is the case the series is convergent everywhere, and this is the case series is convergent only at one point and diverges otherwise. So we prove this as a corollary to the theorem 18 when we also consider the convergence at the endpoints of an interval. There are 6 different possibilities as shown in this figure. So this corollary states that the convergence of the series sigma cn x minus a to the power n is described by one of the following 3 cases. Number 1, there is a positive number r such that the series diverges for x with x minus a mod greater than r, but converges absolutely for this region where x minus a mod is less than r. The series may or may not converge at either of the endpoints x equal to a minus r and x equal to a plus r. The second case, the series converges absolutely for every x, that is on the whole real line. Third case, the series converges at x is equal to a and diverges elsewhere. So for proof, we consider the case where a is equal to 0, that is center is 0. So that we have power series in result which looks like this, centered at 0. If the series converges everywhere, we are in case 2. If the series converge at only one point, that is x is equal to 0, then we are in case 3. Otherwise, there is a non-zero number d such that sigma n varies from 0 to infinity, c and dn diverges. Okay. If we are not in these two cases, then there must exist some number d non-zero number d such that sigma c and dn diverges. Let S be the set of values x for which sigma c and xn converges. So we have a set x where this series is convergent. So the set S does not include any x with x mod greater than d mod. From previous theorem we have already learnt this. Okay. So from previous theorem, that is theorem number 8, series will diverge at all such values. So the set S is bounded. Okay. So the set S is bounded. And if the set S is bounded, it must have a least upper bound, say R. So this is the smallest number with the property that all the elements of S are less than or equal to R. Since we are not in case 3, the series converges at some number b is not equal to 0, and by theorem 18 also an open interval minus b. Therefore, r is greater than 0. So this r is going to be greater than 0. If x mod is less than r, now what if x mod is less than r? Then there is a number c in S. This is S is the set of the points where this series is convergent. If x mod is less than r, then there is a number c in S such that x mod is less than c is less than r, because r is the least upper bound. Since otherwise r would not be the least upper bound. Okay, the series converges at c since c belongs to S. So by theorem number 18, the series will converge absolutely at x. Now for x mod greater than r, so this was the case when x mod is less than r, series is convergent absolutely. So if x mod is greater than r, if the series converges at x, then theorem 18 implies it converges absolutely on the open interval minus x. So that S contains this interval. Okay, because S is a set of all the points where the series converges, contains this interval. Since R is an upper bound for S, again R is an upper bound for S, and this implies x mod is less or equal to R, which is a contradiction. So if Rx is greater than R, then the series will diverge. Okay, so this proves the theorem for the power series centered at a is equal to 0, and we can prove this for center x is equal to a by assuming that x prime is equal to x minus a, and we can redo all the steps with x prime is equal to 0. And in this case, r here is called the radius of convergence of the power series, and the interval of radius r centered at a is called interval of convergence. And the interval of convergence may be open. We have already seen that with in last examples. It may be open, closed, half open, depending on the particular series. At points x minus a is less than r, the series converges absolutely. If the series converges for all values of x, we say its radius of convergence is infinite. Okay, so if it converges only at x is equal to a, we say that its radius of convergence is 0. Right? How to test a power series for convergence? There are few steps to be followed. We can summarize the discussion we have already done in this slide. So first step, use the ratio test or root test to find the largest open interval where the series converges. Absolutely. That is, we have to find this interval. Second, if R is finite, test the convergence or divergence at each endpoint. This is very important. You have to check the endpoints individually. As an example, 3, A and B. Use comparison test, integral test, or alternating test in order to check the convergence or divergence at the endpoints. Number 3, if R is finite, the series diverges for x minus a greater than R. This is also very important. It does not even converge conditionally because the nth term does not approach 0 for those values of x. Now, the operations we can do on power series. Let's have a look at the operations. We can add the power series. We can subtract the power series by the usual way to add and subtract the series. We can multiply two power series, and multiplication of two power series will also result in a power series. Power series can also be divided in a similar way to the division of polynomials, but we are not going to actually give the general formula for this. So here is the series multiplication. If we have a series AX power series sigma a and xn, another power series sigma b and xn, and both the series are convergent, absolutely convergent for some x mod less than r, and let Cn be a naught b naught plus a1 bn minus 1 and so on, then sigma, this can be written as sigma ak bn minus k. Then we have a series sigma cn xn which also converges absolutely to ax bx. That is the product of the sum of these two series for the same region of convergence for x mod less than r, and it can be written in this form. You can verify these tests with the help of examples. So finding the general coefficient Cn in the product of two power series can be very tedious. General term is of course quite tedious, but we can see how it works with the help of example. So here we have a series sigma xn. There is another power series sigma minus 1 to the power x to the power n plus 1 over n plus 1, and if we multiply these two series, we have this series. So first we multiply 1 by x square, we chose this one, and we multiply this one by every term of this series, and then we'll multiply x with with every term of this series with this, and similarly we can multiply and continue in this way. We have this series, and this is also a power series. Okay, so we can also find the value. If both the series are convergent, then we can also find the value of the function this series converges to. So theorem 20. Sigma a and xn converges absolutely for x mod less than r, and f is continuous function, then sigma a and f x to the power n converges absolutely. Okay, on the set of points x where sigma fx mod is less than r. Okay, what we did actually, we replaced x by some fx, right? So if this series converges absolutely and we have a continuous function f, then this series also converges absolutely on the set of points where fx mod is less than r, right? And as an example, we have 1 over 1 minus x sigma xn. We have already shown this. This converges absolutely for x mod less than 1. So it follows from this theorem 1 over 1 minus 4x square. That is, we replaced x by 4x square. So in this case, our fx is 4x square. And this is the series sigma 4x square to the power n. This series is also convergent and is converges to this. Converges absolutely when x satisfies 4x square is less than 1, or equivalently x mod is less than 1 over 2. You can solve this by and get this interval for x. So term by term differentiation, this is very easy. You just have to differentiate the series term by term. If you have a series power series sigma a cn x to the x minus a to the power n with the center x is equal to a and cn are the coefficients, has the radius of convergence r, so it defines a function fx is equal to, since this is convergent, so there must exist some fx such that fx is equal to sigma n raised to 0 to infinity cn x minus a to the power n, and since this is the radius of convergence, so this will converge in this interval, and we can differentiate this function f So the function f has derivatives of all orders inside the interval, and we obtain the derivatives by differentiating the original series term by term. So here is the derivative of the series, and the function f prime x can be written as sigma n varies from 0 to infinity. We just have to differentiate the nth term, n cn x minus a to the power n minus 1. Similarly, we can differentiate it again in order to get the second order derivative. Second order derivative is also a power series, and so on. So each of these derived series converges at every point of the interval where x lies between a minus r and a plus r. So this is an example to find the first derivative and second derivative of the series. So you can do it yourself, and you can check. This is very important. The interval will remain same. Interval of convergence will remain same. Caution. Now, term by term differentiation might not work for other kinds of series. For example, if we have a trigonometric series, sin n factorial x over n square converges for all x, but if we differentiate it, we have this series which diverges for all x. So this is not a power series, since it is not a sum of positive integers, integer powers of x. So the differentiation rule is valid for the power series. So you should keep it in mind. So term by term integration, suppose that we have a series sigma n varies from 0 to infinity, which is a convergent series and converges to fx in this interval, then sigma cn x minus a to the power n plus 1 over n plus 1 also converges in this series. So integral of fx dx is equal to cn x n minus a to the power n plus 1 over n plus 1 plus c. So we can, there should be sigma as well, where x lies between a minus r and a plus r. This region of convergence will remain same. So here is an example of integration. So we have fx, which represents this series. This series is convergent and converges to fx, and we don't know what is the value of fx. Now, term-wise, this series can be written in this form. So, if we differentiate this series, we have this series, and we can find the sum of this series. This is the geometric series, and this is convergent when its ratio r is less or equal, less than 1. So, this series is convergent in this interval. Okay, you can verify this, right? So, let's find the sum. So f prime x is first term divided by 1 minus common ratio. So with the common ratio in this case is minus x square. So 1 over 1 plus x square. That is, the derivative of this series converges to 1 over 1 plus x square. So in order to find the fx, we have to integrate it. So let's integrate it. Integrate both sides. We have tangent inverse x plus c. So our original series fx converges to tangent inverse x in this interval. So it can be shown that the series also converges to tangent inverse x at the endpoints x is equal to plus minus 1, but we are not going to get into this proof. Okay. Well, note that the original series in example 5 converges at both endpoints of the original interval of the convergence, but theorem 22 only can guarantee the convergence of the differential series inside the interval. There is another example of integration. So we have this series 1 over 1 plus t is equal to 1 minus, you can prove it yourself. This is also a geometric series and you can prove this. Now just integrate both the sides. We have the integrate from 0 to x, right? Integrated from 0 to x. So we have to find the interval for which the derivative is going to be this series, right? We have to find a function for which derivative is this series, right? So d by dx of 0 to x, sum f of t dt will give us f of x. That is, if we are going to integrate this and differentiate this integral, we will have 1 over 1 plus x. So in this way, we can find the function whose derivative is this series. That is, that function is called the integral of this series. So integral of 0 to x 1 over 1 plus t, we have to integrate right side term by term, and we have this result. We will plug in the limits, and the left side becomes log of 1 plus x by the fundamental theorem of calculus, as I wrote here. So by the fundamental theorem of calculus, this becomes log of x. A to b, what fundamental theorem we have used? A to b fx dx is f of b minus f of a, where this fx is the antiderivative of this fx. So log of 1 plus x. Log of 1 plus x is equal to this. So this means log of 1 plus integral of this series is going to be this. And the region of convergence will remain same. So it can also be shown that the series converges at x equal to 1 to the number log 2, and I think we have already shown this. But this theorem of integration actually does not guarantee this. So that's all for this section.